You ready? So let's try this again, and I think it'll be clearer. Two key ideas. Number one, all of us have a basic innate understanding of probability, and it sucks as soon as we get anything remotely past basic. That's why we're so superstitious. In fact, later on in this lesson already, I'm going to give you a question where I'm going to ask you to predict the answer, and you're going to find your prediction is totally off when we do the math. Second thing, though, the basic rule of probability is if you can count it, you can solve it, which means eventually we're going to bring our NPR and NCR tricks into it as well. So lesson one, we want to talk about experimental and theoretical probability. I want you to visualize rolling a die. Thank you. What's the theoretical probability of getting a 5? This we all have an intuitive understanding of. Taylor. Okay, our notation then is going to be, how about probability of getting a 5 is 1 out of 6. Does that mean if I roll a dice 6 times, I'm guaranteed to get exactly 1 5? No. What does it mean? Here's what it means. This is the definition of probability. I'm not going to write this down. It's often called the law of large numbers. It says, if you keep rolling this die 1,000,000 times, 1,000,000,000,000 times, 1,000,000,000,000 times, 1,000,000,000,000 times, whatever magic number you want to make up, over the long haul, eventually, about 1/6 of the time, you'll get 5s. So suppose you did this experiment, you actually did it. You rolled it 300 times, and a 5 appears 45 times. What's the experimental probability? The experimental probability of getting a 5 is 45 out of 300. What's that in lowest terms? You can either do that in your head by saying, I think I can divide the top and the bottom by 9, or you can use your fancy fraction button. I don't care which. 15 over 100? It goes lower than that because you can divide by 5, in fact, I think you can divide by 15.
You get 3 over 20.
3 over 20, which is what as a decimal? You need to know how to do this on a calculator. So how do I change a fraction to a decimal on a calculator? Just divide, right? What is it?
15.
0.15?
Yep.
Or 15%. What's 1 out of 6 as a decimal? What is it?
0.16 or 0.17.
0.16 repeating, I think, yes?
Yeah.
So I'll go approximately. By the way, the symbol for approximately is an equal sign that's kind of curvy. That's the way of saying it's roughly approximate equal to. So that's why I did that here. I'll call it 0.167. So when we ran the experiment, we did worse than we should have in theory. However, if we ran this 1,000 times, I would expect that 15% to get closer and closer and closer to 16.7%, 16.66%, 16.666%, 16.66667%. The more I did this, the more I would expect over the long haul my experimental to match my theoretical. Not guaranteed. Nothing prevents me, Darian. There's no universal law that says I can't roll a die 300 times and get 300 5s in a row. It's just unlikely. You can kind of force feed it, though. Let's suppose you take 1,000 people and you have them all flip a coin. On average, how many would get heads? If you have 1,000 people and you have them all flip a coin, on average, how many would get a head? So you got 500, you take those 500 that all got heads, you have them all flip a coin. On average, how many would get a head now? 250, have them all flip a coin. On average, how many would be left now if you kept the heads? 125, have them all flip a coin on average around 60, have them all flip a coin on average around 30, have them all flip a coin on average around 15, have them all flip a coin on average around 8, then 4, then 2. But you know what? At the end, there's going to be one fella or one woman, one person who has flipped a coin and gotten like 9 heads in a row. Is that magic? Is that what? No, that's expected. In fact, that's almost guaranteed with that experiment. So it's called the law of thinking that you're special. When people win a lottery and they say, oh, I felt like my numbers were lucky. No, you're the person who was guaranteed once we eliminated all the losers, someone had to win. You're not special. Here's a picture of a deck of cards. How many suits are there? 4. How many cards in each suit? 13. I did this on purpose because I do want to ask you card questions. I think they're cool. I think it's nice to know a little bit, especially because poker and gambling are fairly big in our society right now. So you will need to be familiar with what a deck of cards looks like. Suppose one card, how many cards? No. Suppose one card, how many cards are we drawing? 1. Eventually we'll say, hey, what if you're picking 3? What if you're picking 5? But we're going to start out with 1. Is drawn from a deck of 52 cards. Now, whenever I say this, Oscar, let's assume it's a well-shuffled deck. I used to, before every 52, include the words well-shuffled deck of 52 cards. It just started taking up too much space and typing. So we're going to assume it's well-shuffled. What's the probability that it's a face card? If you can count it, you can solve it. What I'd like you to do with your pencil is I'd like you to circle all of the face cards. There they are. Those are the face cards. In terms of symbolism, what would be a good letter to use for face card? F is what out of what? Give you a hint. 12 out of 52. I'll change colors because I can. You don't have to. B says, what's the probability that we're a red ace? In fact, you know what? I'll do this one in red. Now, later on, I'll teach you how to do this without circling because this is really saying what's the probability that you're red and an ace. And we have talked about how and means multiply. But for what it's worth, I think there is my red aces. How many? Out of? Which in lowest terms is what? One out of 26, right? I did, because we've done some of this already, I did say and means multiply. You could also say, what's the probability that's red and an ace? There are 13 out of 52 red cards, and ace, you know what? I don't know if I can use a multiply for this one here. I think it's going to be a count. I'll take that back. Let me take that back. King. I'll change colors again. I'll go black. Out of? If you can count it, you can solve it. The tricky part is counting. First of all, the tricky part is interpreting the question. These are pretty obvious. Sometimes it gets tougher. And the tricky part is counting it. If you're in the thousands or in the millions or in the trillions, which we're going to get with card questions. Next page. This gives us our definition of probability.
Did you make it go down so I didn't make true?
Can you reduce it? If you want to, I'm going to choose not to reduce because it's going to be easier to have a common denominator. And for card questions, most of the time our common denominator is going to be 52 already built in. But you're going to see in the homework, they're going to reduce the answers. So then yes. But I will never reduce in my answers. Taylor, this gives us our official definition of probability. The official definition of probability says this. If an experiment has n outcomes, of which r are favorable. By the way, can you do me a favor? Can you underline the phrase equally likely? That's important right now. Grayson later on will say, hey, what if they're not equally likely? And we'll find there is a workaround. But for now, we're going to assume each of them is equally likely. if there's n equally likely outcomes, of which r are favorable, the probability is defined as r over n. Or as you're going to hear me say fairly often, the number of successes divided by the number of outcomes. One of the tools that I want to give you, which ranks right up there in my mind with the Scrabble bag and the bucket from last unit, is a tree. And this is one of the reasons I decided to move away from the workbooks approach. They brought in trees in that very last lesson, and I could see you guys weren't getting how useful they are. Calculating probabilities using tree diagrams with equally likely branches. And here's our first question. This is a fairly easy question, but I told you all of us have a bad sense of probability. So here's the question, and what I'd like you to do over here in the margin is write down a guess. The question says this: as a fraction, what's the probability that in a family of 3 children, exactly 2 of them are girls? So suppose you meet some people, you know they have 3 kids, you don't know the genders of their kids. What's the probability that there are exactly 2 girls? I'd like you to make a guess right here, please. Write down what you think as a fraction, what out of what. No one else is going to see this. What's the probability that in a family of 3 children? In particular, I want you to think about what would be on the bottom. So if there's 52 cards in a deck, what's going to be in the bottom of this particular fraction? 3 children, 2 girls. A 5? A 6? A 12? A 10? A what? Okay, here's our solution with a tree. We're going to assume that the odds are 50-50 boy or girl, which actually in the world isn't quite true. As I understand it, there are slightly more, I think it's slightly more females than males. I think the birth rate around the world is 50.001 females to 49.99 males. But you know what, Jordan, let's assume we're 50-50. We're going to draw a tree diagram. And our diagram is going to look like this. We're going to have one level for kid number 1, another level for kid number 2, and another, write this down, level for kid number 3. So the tree starts out. The first kid can be a boy or a girl. Heck, let's even call it B1, G1. 50-50 chance. What can the second kid be? What can the third kid be? This is an example of a 3-level tree. Now, I'll be honest, I don't usually do a 3-level tree. I always, if it's 2 levels, use a tree. Sometimes if it's 3 levels, I use a tree. I don't go much beyond a 3-level tree. So here's what it says in the instructions. Draw a tree diagram, check, to represent the possible arrangements of boys and girls in a family of 3 children. Each branch is equally likely. Why? What are our assumptions? We're assuming boys and girls are born at a 50% rate. They aren't quite, but we'll assume they are. How many branches contain exactly 2 girls? Let's circle them. That branch. That branch. that branch. Yes? How many branches contain 2 girls? 3 of them. Divide that number by the total number of branches to determine the probability. The probability of 2 girls Did anybody guess 3 out of 8? I haven't had anybody yet. That's a fairly simple question, but most people get this way off, way wrong. I have no clue. And sadly, this is also, again, why our society is so superstitious. We look for coincidences that aren't there, or we don't recognize things that really aren't that unlikely, that it's not a big deal. Example 4. When the pointer is spun twice, find the probability that you win a total of $10. How many times are we spinning? Once again, how many times are we spinning? I can do this with a 2-level tree. We have first spin, second spin. What can you get on the first spin? What are the possibilities? So I'm going to have a 4 branch, 1, 2, 3, 4, and it's going to end in 0, 5, 10, 20. What can you get on the second spin? It's going to be 0, 5, 10, 20, 0. I got to kind of shrink this down. 5, 10, 20, 0, 5, 10, 20, 0, 5, 10, 20. Sorry I can't draw it much bigger, but hopefully you get the gist and you can draw it yourself. Hopefully, Laura. I hope. Probability that you win $10. First of all, what's it going to be out of? How many outcomes are there? 16. We'll talk about how you can use the fundamental counting principle to get that later as well, but 16. Of those, in how many do you win exactly $10? Now, I don't want to wreck my tree, so I'm not going to use the circle method. What I tend to do is I put check marks underneath the branches that are successful. I'm going to say yes, yes, yes. That's it, yes? What out of 16? There's my answer to part A. What about part B? The same number comes up. Okay, I'll change colors because I can, but if you haven't changed colors, just scribble out the check marks and do new ones in the row beneath. You know what? There, 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 and there, right? What's the probability that you get same number coming up? Which is 1/4, but I don't care. If you can count it, you can solve it. Trees are handy. Example 5. When 2 bills, how many bills? 2 are randomly selected from the pot without replacement. That's going to be important. Find the probability that you win a total of $10. I'm going to do the tree beneath the pot because I got more room here, and I'll do my answer over on the left. So my tree is going to be, I guess on the first draw, how many outcomes are there? So it's going to be 1, 2, 3, 4. How many outcomes will there be for each branch on the second level if I'm not replacing the bills? So it's going to be, I guess, a 5, a 10, and a 20, a 0, a 10, and a 20, a 0, a 5, and a 20, a 0, a 5, and a 10. First of all, how many outcomes are there? 12. Of those, how many do you win exactly $10? Here, here. Oh, I think that's it. Yes?
Yep.
2 out of 12. Now, one thing we don't look at, Kyle, and I wish we did, but it's not part of the curriculum, I may add it next year just because I'm a nerd, is the following question. On average, how much will you win playing this game? It's called the expected value. And it helps you decide whether or not to gamble. If on, I'm just making up the numbers, if on average you win $6 playing this game and they're charging $5 to play, you keep playing this game until you go broke. Well, you're not going to go broke over the long haul. The more times you play, the more likely it is you come ahead. No casino runs that way. Most casinos have an expected value win of like 10 cents and you're paying $1. Which means once in a while they'll pay out, but most of the time they're coming out ahead. Your first batch of homework that you can now do is this, but we're going to move on to lesson 2. Related events, a continuation. So turn the page. So a list of all of the possible outcomes we call a sample space. A sample space. So there's our pot. If we select one bill, what's the sample space? What are the possibilities if I select one bill? 0, 5, and 10. Boy, that's a bad bracket. Let's try that last one again. Not much better, but a little better. What if instead of selecting one bill, what if I was selecting 2 without replacement? What would the sample space be? 0, 5, comma, 0, 10, comma, 5, 0, comma, 5, 10, comma, 10, 0, comma, 10, 5. Right? To be very obvious, what if I was selecting 3 bills? What would the sample space be? 0, 5, 10. Okay. What's the probability that a $5 bill is selected? Very basic. How many 5s are there in the pot? How many outcomes are there? This one seems to be built into us. Basic probability understanding seems to be wired into us. By the way, I think probably in terms of an evolutionary biology, the reason we're so superstitious, it may have been an advantage for our ancestors to be more paranoid about danger, to be overly paranoid about danger, because then maybe we avoided it even when we didn't need to avoid it, so that unlikely events didn't happen to us. They happened to the people who didn't pass on their genes to the gene pool. Example 2. One bill is randomly selected from pot A and one from pot B. How many bills are we selecting grand total? 2. It says use a table to construct a sample space, use a tree diagram to construct a sample space, which is easier. I'm going to do the table over here. I'm going to have pot A which has outcomes 0, 5, and 10. And pot B, which has outcomes 5, 10, and 20. And here are the outcomes. You could have 0, 5, 5, 5, 5, 10. Sorry, 10, 5. I'm doing pot A first, aren't I? By the way, if you listed pot B first, Brianna, I'm okay with that as long as you're consistent all the way through. Taylor, you going to make it? Okay. 0, 10, 5, 10, 10, 10. 0, 20, 5, 20, 10, 20. Jake, you okay with how I filled that in? Right? How many outcomes are there? Count. 9. Yeah. I could have done a tree, by the way, where this first level is pot A, which can be 0, 5, and 10. And the second level would be pot B, which can be 5, 10, 20, 5, 10, 20, 5, 10, 20. Which is easier? It depends on how many outcomes there are, Mark. If this was, instead of 2 pots, 2 dice, I'd be 6 across and 6 down. How many outcomes would I have? If I was 6 across and 6 down, how many outcomes would I have? 36, fitting in 36 tree branches is unwieldy. In fact, usually right around 9 or 12 is where I have my cutoff and I say, I'll do a table, or I'll find some other way. So there's my sample space. We can now answer questions. B says, what's the probability that the sum is $10 exactly? Jake, what did you tell me this was out of? What were the number of outcomes? 9? Okay. Let's circle in the chart the ones where the sum is $10. Here and here, right? So, Jake, what's going to be on the top of the fraction? 2. And you could have done it this way by saying, okay, it's got to add to 10 there and there. Tables, charts, and trees is what we're going to start out with. This alone gets us a long way. Hey, let's do a card question. One card is drawn from a well-shuffled deck of 52 cards. How many cards are we drawing? 1. Use the graphical display to find the probability of getting a red card. You know what? I'm going to circle the red cards in red. You can circle them in pencil. The red cards are those. Jordan, how many did I circle? More specific, how many did I circle? Out of? Okay. If you can count it, you can solve it. How about Jack? You know what? Let's circle, I'll change colors, all the Jacks. How many Jacks? Out of? By the way, is the event Jack mutually exclusive from the event red card? Or is there some overlap? And you can see what graphically it becomes much more obvious. What's the probability of getting a card that's not a jack? Now we have a symbol for not. What's our symbol for the complement? Can you tell me the answer, please, without counting?
48.
48. Not a 52. Did you count?
No.
No.
Subtract.
Okay. By the way, in any deck of cards, is every single card either a jack or not a jack? So what should these two here add to? 1. Do they add to 1? You get 4 out of 52 plus 48 out of 52, which is 52 out of 52, which is 1. And Taylor, that's why I don't reduce. Just that's one of my built-in error checks that I use all the time. I glance at it and I say, have I missed anything? They don't add to 1. I've missed something. And it's nicer if they're common denominators already. Okay? Red card and a jack. Red card and a jack. I think that is that little subgroup right there, isn't it? How many, Mac? Out of? Red card or a jack. Now, or means one or the other or both. And one way of doing this would be to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 22, 24, 26, 28 out of 52. We'll talk about how to get there with a tree or with a formula in a bit, but for now you can get there by counting. This brings us to related events and complements. The event that A does not occur is the complement of event A and is denoted by, now you can denote it A bar or, Jordan, you can denote it A apostrophe. Both are acceptable. In foundations, they're using the apostrophe notation from set notation. In the old Math 12 course, we used to use the bar notation from probability notation. And if you add up the probability of something not happening and the probability of it happening, it has to add to 1 because every single time, Brianna, something happens or it doesn't. Which really means the probability of something happening is also equal to 1 minus the probability of it not happening, which is how Taylor was able to get that 48 out of 52 without counting. The event A and B occur, that both occur, is denoted by A and B, and as a picture, it's that section right there. The event that A or B or both occurs, when I say A or B, I will always mean A or B or both, and it's that shaded in area, the overlap as well as the rest of each oval. This here is the probability of not A or B. Or in English, neither. The area outside the two circles is not or neither. Not or. Okay? Turn the page. A black die and a white die are rolled. There's a lovely chart that I did, but that line moved up and is partly cutting through the numbers, and it irritates me, but I'll fix it later. This black line here was supposed to be half a space down. Anyways, consider the following two events. The sum of the two dice is at least 9. The black die is 1 less than the white die. I am on your test going to give you a 2-dice question, and the approach for any 2-dice question is use a chart, go 6 by 6. 6 across, 6 down, list the pairs. It's 36 possible outcomes. It takes you about 60 seconds to write them all. It goes pretty quick. It says use the sample space to find the following probabilities. What's event A? What does it say? What's event A? Yeah. Can you wait for about 5 more minutes, please? Sorry, what's event A? The sum is 9. Let's circle which ones up there add to 9. And usually with a chart, you'll notice a pattern. I think it ends up being this diagonal right here, yes? Everything in there adds to 9. So, Oscar, what's the probability that the two... Oh, wait a minute. It says at least 9. At least 9. So, that and that and that also qualify. In fact, that whole bottom corner qualifies. At least 9. Oscar, what's the probability that when you add the dice up, it adds to 9 or higher? What's it out of going to be? Sorry? How many outcomes are there? How many are circled? Is it 9? 4 plus 3, 7. I don't count carefully. Is it 10?
It's 10.
10 out of, yes? Oscar, yeah? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes? Event B. Laura, what's event B? What does it say? The event B is what?
The black die is 1 less than the white die.
Okay, the black die is, which one? Black die is the first one. So that the first die is 1 less than the second die. Let's see. Yes? No, 1 less, not 1 more than. Sorry. 1 less. Here. Where else? What, comma, what?
2, 3.
Oh, here, here, here. That diagonal there. What's the probability of B, Laura? What out of what?
5
Yep.
36.
Yep. Okay, folks, what's the probability of A and B? Can you see it? 2, because 2 are circled twice out of 36. What's the probability of A or B? 13. Did you count or were you clever? Did you go 10 plus 3? Okay. By the way, later on, you'll see from this why it's the first plus the second minus the overlap. You're going to see actually you're sort of double counting if you're not careful. But yeah, 1, 2, 3, and 10. 13. What's the probability of not A? Preferably without counting. In English, what does not A mean in English? Well, first of all, what did A mean? Brennan, can you read to me what the event A was? So what's the opposite of that, or the complement of that?
The sum of the 2 dice.
I heard that, and then I heard this. Are those two the same thing? Are those two the same thing? Is less than 9 the same as at most 9? No. One of those is wrong. So if the sum of two dice is at least 9, what's its complement? Less than 9. How could you change Brandon's statement so that it's correct? The sum is at most what? Right? Does it make sense? By the way, one of the most common errors in probability, you accidentally double count one group without being very, very careful. You're double counting the 9 twice with the complements, right? Last one. If each of the 13 outcomes in the sample space is equally likely, this is important. Later on it won't be. Later on we'll find a workaround. Find, if you can count it, you can solve it. What's the probability of A? Careful.
4 over 13.
4 out of 13. Why isn't it 3 out of 13?
There's one in the middle.
Okay, that's part of A as well. What's the probability of B? What's the probability of not A? 9 out of 13. What's the probability of not B?
8 out.
What's the probability of A and B? The overlap? A or B? This, and this, and this, right?
Yep.
Not A and B. Sorry, what? 12 out of 13. Not A or B. Can you see where the 5 are as a picture? Right? It's those. That's not A or B. That's neither. So your homework for now, could you please go back if you haven't already, and even if you have without understanding, could you do the homework from the end of lesson 1, which was page 127, number 1, number 4, and then 6 to 11? And then try from the workbook, page 141, number 1 and 2.